those that just joining us. We'll continue with the kinetics of the batch system. And as usual, please feel free to interrupt if you have challenge understanding certain aspect of the module. Okay, we were looking at this graph yesterday. First, are you able to hear me, class? Are you able to hear me? Right, thank you, Tai. We're looking at this graph, the micro304 grid curve. We said that it applies to the batch system. Okay, I repeat, you're going to have these phases only in the batch system, not fed batch, not continuous. Right? Take note of that this curve is applied or is obtained only when production is carried out in a batch mode. Right? This graph is obtained only when production is carried out in the batch mode. Now, we learned yesterday it goes through several phases. You have the lag phase, you have the acceleration phase, then you have the exponential or log phase, you have the deceleration phase, eventually you have the stationary phase, and ultimately the dead phase. Okay, we've already seen a little bit what takes place, the physiological changes that take place at the lag phase. We've also seen the physiological changes that take place at the exponential phase, and we'll learn that at the deceleration phase, cells are facing nutrient starvation, and at the same time, there may be accumulation of toxic substances. One other thing we'll learn is that we'll learn that there are different kinds of products produced at the exponential phase, and you'll have a different set of product produced at the deceleration and stationary phase. Now let's continue on this acceleration, sorry, on the stationary phase. Now, during the acceleration, during the stationary phase, the number of cells that are still alive, cells are dying, but cells are multiplying. That could be that scenario, such a way that the overall cell balance, if you check the cell biomass or cell count, it will remain relatively stable. Okay, at the stationary phase, it could be a scenario in which the number of cells dying is equivalent to the number of cells produced. In that case, you have a constant number of cells in that phase. And again, we said that you may have some product similar to those or the deceleration phase that also produce, maybe in lower amount, that also produce during the stationary phase. And very often, the same parameter, the same factors that have triggered the deceleration phase would be the same parameter that will trigger the stationary phase. For example, if it is the depletion of nutrient that has led to deceleration phase, it's the same depletion of nutrient that will trigger the stationary phase. Yeah, some activities that take place during the stationary phase, you have a very slow metabolism, and you have production of antibiotics, and also endospores are formed during that phase of that stationary phase. And just like I mentioned earlier on, those factors that have triggered the deceleration phase are likely to be those involved in the stationary phase. If the deceleration phase was triggered by accumulation of toxic substances, it's highly likely that the stationary phase will be triggered by the same factor. Okay, take note of that as well, that the same factors that have triggered the deceleration phase are likely to be involved in the stationary phase. Okay, you can highlight this section in your material. Obviously, you're going to reach a dead phase, scenario in which cells are not multiplying, but they are dying, right? After the deceleration phase, you enter the stationary phase. And after the stationary phase, you enter the culture enters the dead phase. Dead phase, cells are not multiplying, but they are dying. The number of cells is virtually reducing. Now let's begin to see a little bit how do you quantify growth. Okay, how do you quantify growth? There are several approaches to quantify growth. You can quantify growth based on the change in the biomass concentration in the reactor. For example, when you have a reactor, you want to have a mechanism to estimate the amount of cells in the reactor. That will guide, for example, in providing the right concentration of nutrient in order to ensure that cell growth and produce your desired product. You want to know whether cells are actually growing or not. And you can only achieve that if you're able to quantify the cells in the reactor. Okay, this is extremely important. You want to have a mechanism to know the population of cells in the reactor. This is what the section we're going to go through now. Then I really want you to pay attention and understand how we go through the different calculations to achieve cell quantification in the reactor. Okay, now let's first understand a couple of things here. Cells, bacteria divide by binary fission. Scenario in which one cell, as you can see in this diagram, one cell will divide to give two daughter cells, which in turn will divide, the two daughter cells will divide to give four daughter cells. Then the four daughter cells will divide to give 8 daughter cells, and so on and so forth. That is, we have that kind of binary fission that takes place in cell division. And if you start, for example, with one cell, after a period of time in your reactor, you want to be able to know what is the approximate number of cells or biomass concentration that is in the reactor. Of course, that will guide you in making some decisions. For example, should I add more nutrient in the reactor? Should I provide more oxygen, and so on and so forth? And can only achieve that you have an idea of the cell concentration in the reactor. Now, let's look a little bit at the calculation. In other words, you start from, let's say, a population of cells that is N0 or N0 to 2 daughter cells, 4 daughter cells, and so on and so forth. The same expression can therefore be represented by 2 to the power of n multiplied by the initial cell concentration N0. That implies that at any point in time, let's say time t, you want to know how many cells are in the reactor. Based on this binary fission concept, you can apply this formula. T will be the time at which you want to find the number of cells in the reactor. Taking into account that cell divide, which you have a single cell that gives rise to 2 daughter cells give rise to 4 cells, and so on and so forth, as shown in this diagram. Right? That is, you go to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of n. Now, if you apply this concept, that tells you that the number of cells in the reactor at the time nt equal n0 multiplied by 2 to the power of n. N is what? The number of generation, or the number of doublings. Let me repeat again. Based on this diagram, the concept of cell division, you want to know how many cells in the reactor at time t. If you know the number of generation or number of doublings that has taken place, and you know the initial cell number available in the reactor, you apply this formula, nt equals n0, that is what was there at the beginning, maybe 1 cell or 2 cells thereabout, multiplied by 2 to the power of n. 2 because of the binary division. N corresponds to the number of doubling. Right? Now, just take note of a couple of things here. If you plot, of course, growth of cell takes place exponentially. If you follow this diagram a little bit again, you're going to have an exponential growth. It's not a simple arithmetic growth. You're not going from 1 cell to 2 cell to 3 cell to 4, 5, and no. You're going from 1 to 2, 2 to 4. That is, you're going to have a kind of exponential augmentation or exponential growth, not arithmetic growth. Now, what you have here is, if you decide to plot the number of cells, cell number, against time, you're going to have a graph that shows this kind of arithmetic growth. Remember, if you just plot the number of cells, not the log number of cells, your diagram will show this kind of arithmetic growth. However, if you plot the log of the number of cells, using log 10, for example, if you plot the log of number of cells, you're going to have a straight line like this. Let me repeat. If you plot the number of cells only versus time, which is an arithmetic growth, you're going to have this kind of behavior. However, if you plot the log of the number of cells against time, you're going to have this kind of straight line. Keep in mind that cell divisions takes place in the exponential pattern, not arithmetic pattern. You go from 1 cell to 2 cells, then 4 cells, then 8 cells. If it were an arithmetic growth, you may go from 1 cell to 2 cells, from 2 cells to 3 cells, 3 to 4, 4 to 5. No. Our knowledge of biology tells us it grows in exponential fashion. Yeah, just like said previously, if you plot the log of cells, cell number versus time, you're going to have something resemble a straight line. However, if you plot the arithmetic number of cells without finding the log value against time, you're going to have this kind of shape, the green one. Just a couple of things to refresh your memory. You learned in your previous high school this little computation of log of x times y equal log of x plus log of y. Just take note of that because we're going to use it in the subsequent slide. I'm just trying to refresh your memory that log of x divided by y equal log x minus log y. Log of x to the power of r is the same thing as r times log of x. Okay, just take note of all these three basic computation to refresh your memory. Now, let's take note again of our cell growth as illustrated in previous slide, that the NT, the number of cells at time t, equals n naught, the initial number of cells multiplied by 2 to the power of n. And we said n is a number of doublings, the same thing as number of generation. And T is the time interval within which we want to carry our computation. Then you have a new term here. TD is the time it takes to achieve one doubling. That is a time to move from n naught to 2n. I repeat, TD is a time it takes for a cell to complete a cycle. Is a time it takes to achieve one multiplication or one division. Is a time it takes to go from n naught to 2n naught. Is a time it takes to go from 4n to 8n. That's stands for your TD. In other words, the number of generations or number of doubling is equal to the entire duration of the process divided by the time it takes to carry out to produce one generation. Let me repeat again. N, which is the number of generation, equals the entire duration of the fermentation divided by what it takes for one cell to grow and divide. That is a doubling time. Now, you now have two terms here. N, how to work out your N, which is the time of fermentation. Let's assume that a fermentation has lasted for 60 minutes. And the doubling time is 20 minutes. How many generations will have been produced within that time frame? Class, if the process time is 60 minutes, 1 hour, And the problem says it takes 20 minutes for a cell to grow and double. What will be the n value? How many doublings or how many generations will have been produced within that time frame? 3 generations. Why? How do you achieve that? Simply by dividing the 60 minutes, which is the entire duration of the fermentation process, by 20 minutes, which is the time it takes for the cell to grow and double. Now, how do you achieve that? How can you obtain n? The value of n can be obtained by solving the equation nt equals n naught multiplied by 2 to the power of n. Okay, by applying the log for the log, by applying the log parameter on both sides of the equation. Now, based on the previous slide on log manipulation, we learned that log of nt equal log of n naught plus log of 2 to the power of n. And you could balance the log of n naught to the other side of the equation. That gives you n log of 2 equals log of nt minus log of n naught. And you can easily extract the n value, which will be equal to log of nt minus log of n naught divided by log of 2. Now, that's how to obtain, again, your number of doublings or the number of generations by deriving from the initial equation given to you. You've achieved this by simply applying the log on both sides of the equation. And through log manipulation, we arrive at n, the number of doublings, equal log of nt. That is the time of fermentation, the duration of fermentation, minus log of number of initial cell. It is 1 cell or 2 cells divided by log of 2. That gives you the idea how to find your number of generations or number of doublings. Now, something I would like to take note of this. Class, take note of this. I'm going to show you a couple of things now. Highlight this statement that this applies at the exponential phase of growth. Remember, binary fission takes place when cells are growing exponentially. Cell at the exponential phase. Now, let me ask you a question again. If I said a process, the entire process lasted for 70 minutes. Listen very well attentively, because it's not far from what I can give you in the exam. If I said the entire process lasted for 70 minutes, and the lag phase was 10 minutes, the exponential phase was 60 minutes. The doubling time is 20 minutes. How many generations of cells will have been produced within that throughout the fermentation period? I repeat, the entire process lasted for 70 minutes with a lag time of 10 minutes and the exponential growth of 60 minutes. The doubling time is 20 minutes. What is the value of n? The number of doublings, the number of generations. What's an idea? Sorry, Quan, I didn't get you. How many what's the value of n?
3.
3. Why? Because we did not take into account the lag phase. Am I right?
Yes.
Great. That's why we said this formula applied at the exponential phase. You assume that at the lag phase, cells are basically not growing. Okay, I'll come back to this. Now, let me just give it to you now. Take 1 minute, work out this question. We're going to take let me give you 2 minutes. Okay, everybody, I will call you by your name. You tell me what you have obtained. Class, we have 2 minutes to solve this. A batch fermentation process is initiated with a single bacterium with a weight of 10 to the power of minus 12 grams. The exponential phase lasts for 48 hours with a doubling time of 20 minutes. What is the weight of the progeny produced? That is, what is the final weight of the cell in the reactor? A batch process. I want everybody, I'm going to call you by the name, right? You tell me. If I call you, I want to see what you have obtained. If it's a wrong answer, just tell us what you have obtained. You have 2 minutes to work it out. Okay, what have you, I could see that 2 people have, because as I'm going to ask you what you have obtained, I could see 3 people have decided to disconnect from the system. That gives me, it's actually time for me to take this recording as an attendance, okay? I'm going to take this recording of 23 people as an attendance. I could see 3 people have decided to disconnect because I said I'm going to ask you to give me your answer, right? Now, I've seen the time. The time is exactly 8:13. I'm going to check the video, and 8:13, those connected will serve our users for today's attendance. Having said that, who has got the answer to that? Class, anyone? Have you got any answer? $31. Okay, we're going to check it very soon together, Tai. Who else has obtained what? Okay, let's go through it together, okay? Let's see, what do we have here? We said a batch process initiated with a single bacterium. That is, we have our N initial, N0, which is 1. What other parameter is available? They said TD, the period required for the cell to double, that is, when TD is 20 minutes. Our doubling time is 20 minutes. The period required for the cell to double, to have produced 1 generation, is 20 minutes. That's our parameter that we have. They also said that the process lasted for 48 hours. Based on that, we can obtain N, the number of generation. Are we on the same page, class? 48 hours times 60 minutes, divide by 20, the time it takes to double. That gives us our N, which is 144. Now, if you have N, which is 144, you basically apply the formula learned in the previous slide, that NT equals N naught times 2 to the power of N. We've also obtained N, the number of doublings, by dividing the entire fermentation, the duration of the exponential phase, by the time it takes to double, which is 20 minutes. And in so doing, we get our N, which is 144. If you substitute it to the formula NT equal N naught times 2 to the power of N, we're going to have this. In other words, of course, we know that N naught is 1. Tai, is this value that gives you, did you arrive at this scenario? Who among you, I mean the class, the entire class, who reached this scenario here? Who was able to compute this way? Right, that's great. Kwenda and Tai, that's great. Yeah, no, Lutando, that's also fine. I'm happy that you're able to grab it. Robile, that's perfect. Okay, let's proceed. Now, if you look at the previous computation, what you have, let me check the time to be sure that we're on the same page. Okay, let me take just 5 minutes of your time, then I'll release you. Then we're going to have a face-to-face lecture at 11:25. Okay, but before getting there, I decided to take this lecture in the morning time because I'm sure you may see in your, to give enough time, but 11:25 face-to-face lecture on campus. Now let's have a look at this. In the previous slide, we talked about cell number, right? Although it is practically possible, it's theoretically possible to do what we've done in the previous computation. But you got to agree with me that it may not be the right approach to quantify cells in the machine, in the reactor. Why? Because when you are counting cells, they will have different sizes. Okay, we have some that are still at early phase, some are dividing already, and so on and so forth. Don't you think it would be much more suitable or more appropriate to actually use cell mass rather than cell number? Cell number, you have 1, 2, 3. Cell mass, you take the weight of the cell to quantify the cells in the reactor. That is, rather than saying that your reactor has 1 billion cells, it would be much more appropriate to say that your reactor has cell concentration of, let's say, 10 grams of biomass per liter. Because in so doing, you are sure that you have taken into account the entire mass of the cell, not the cell number. Cell number, you may have smaller cells, bigger cells, but cell mass will give a much more suitable representation of the state of the reactor. Now, cell divide asynchronously. Thus, a population makeup of cells of different sizes. Therefore, rather than cell number, cell mass is very often more preferred to use for industrial processes. That is, industrially, rather than cell number, you're going to encounter very often the biomass concentration, X, not N. Now, again, the formula that helps to understand the biomass concentration over time is similar to the one used to express the cell concentrations, the cell number. XT stands for the cell biomass concentration at time t, which is equal to the initial cell concentrations multiplied by the exponential. Mu is referred to as a specific growth rate, which is expressed as the reciprocal of time. And T is a process time. Helps to estimate the cell biomass concentration in the reactor or in the flask at time T is equal to the initial cell concentration exponential mu T. Of course, it's similar to the same formula used to express the cell number over time, which you have covered in the previous slide. Now, the specific growth rate, the new terms that we have studied, that we have learned, mu can be interpreted as a fraction of the cell produced per unit time. I would like to underline this. Okay, underline it, write it in your book or underline it. That mu is a fraction of the biomass produced per unit time. And here's an example. If mu is 0.3 per hour, that will imply that every hour the biomass will be approximately increased by 30%. That's how to interpret the term mu. Okay, I'm going to stop here. Allow you to take to rest a little bit. Then we meet at 11:25 for the second phase of the lecture. Okay, and I really would like you to attend, because we're going to see a couple of things that require that we need to understand for us to complete the section on the batch kinetic. Okay, 11:25, we should be able to complete the section of batch kinetics. Thank you.